So as Alex said, I'm at the UCLA Business School and Medical School. My background is in behavioral economics, and I also do work in genoeconomics, which is about the genetics of behavior. What I'm going to be talking about is the strength of evidence from statistical significance and p-values. And so it actually relates to two different parts of the roadmap. The first topic, the strength of evidence from statistical significance, is about study design. And so it relates to pre-registration, pre-analysis plans, planning power, and generally thinking about the proper design of a study in order to have strong evidence coming out of the study. And then the other topic is the strength of evidence from p-values, which is what you get after you do the analysis. And so that's so that comes later in the process once you've analyzed the data. And you know, as Alex alluded to, I'm happy to take questions throughout the talk. I'm going to also leave time at the end for questions, but please interrupt with questions. I'd love to have a conversation as we go. The setup for what I'm going to be talking about is entirely standard. You're all familiar with it, but just to make sure we're all on the same page, I'm just going to walk through the kinds of terms and notation I'm going to use. We're going to be talking about a context where we're testing a null hypothesis, that some parameter value theta is 0. The way we test a null hypothesis is we create a test statistic. You know, what that is going to depend on the test we're running, but it's some test statistic t. I'm going to talk about a one-sided test for most of the talk, just because it's going to make things conceptually easier, but you know, things will also work with two-sided tests. So with a one-sided test, that's going to mean that the p-value is the probability that the test statistic is bigger than some, is that, you know, for some actual value of the test statistic, the observed value t obs, it's the p-value is the probability that you would get a test statistic at least as large as that under the null hypothesis. The two-sided test case, we'd have to take into account the possibility that we also get a t statistic that's small enough. So it's going to be simpler to just deal with the one-sided case. A significance threshold, I'm going to call alpha. And what a significance threshold alpha means is that we're going to say a result is statistically significant. We're going to reject the null hypothesis if the p-value is smaller than alpha. We can show that, you can show that the type 1 error rate, which is the chance that you declare a result significant when you shouldn't have, when the null hypothesis was actually true, that probability is alpha. So it's both, so the significance threshold doubles as the chance of making a type 1 error. And power refers to the probability that you get a significant result if the alternative hypothesis is true. That is, there really is an effect. And I'm just going to, for simplicity, assume that the alternative hypothesis is equal to some particular value for the parameter theta. So it might be that, you know, some value of theta you consider to be practically significant, or, you know, of real world importance. The amount of power, the level of power, is going to be jointly determined by your significance threshold and the sample size, and of course the alternative hypothesis. So if you have a smaller significance threshold, then for a given sample size, your power is going to be lower. It's going to be harder to reject the null hypothesis, even if the alternative is true. And for a given significance threshold, the larger your sample size, the greater your power. So this is it. This is the context I'm going to be talking about. It's the paradigm of null hypothesis significance testing, and the reason I'm going to stick within that paradigm is that that's what's most common in most of the kind of data analysis that most of us do. But the perspective I'm going to be taking in this talk is from a field of statistics called Bayesian hypothesis testing. So what that means is, even though we're going to be talking about null hypothesis significance testing, which is kind of frequentist approach to statistics, we're going to interpret that approach from a Bayesian perspective. And so hopefully that will give you some different perspective, maybe some new insights into this approach, even though it's an entirely familiar and pretty basic approach to statistics. So for comparison with the kinds of conclusions I'm going to draw later, I want to just remind you of the common practice that we see most of the time when people apply null hypothesis significance testing. That is, people set the significance threshold at 0.05, and that's not even a question, that's just taken as given. We treat findings where the p-value is less than 0.05 or reaches the significance threshold of 0.05 as providing strong evidence for a true effect. And we often ignore power altogether, except when we have to talk about it, for example, for grant proposals. But certainly after we do the analysis, we don't talk about power anymore. And to the extent we do worry about power or do calculations, we typically have some particular threshold, like 80% as the power we're aiming for. So what I want to talk about is some a way of interpreting this approach that might give us a principled way of thinking about what we ought to be doing for things like significance thresholds and amount of power we should be aiming for, and how we can think quantitatively about the actual strength of evidence from p-values less than 0.05 or p-values equal to a particular value like 0.05. So in the first part of the talk, I'm going to talk about statistical significance and power, and that's about study design. And then the second part of the talk is going to be about particular p-values, and that's really for interpreting results once you have data. So the key question for thinking about the strength of evidence from statistical significance, which means a p-value less than 0.05, is this question: if we get a statistically significant result, what does that tell us about the odds or the relative likelihood of the alternative hypothesis relative to the null hypothesis? So we can calculate that using Bayes' rule. So here's what I have at the top here is the probability of the alternative hypothesis being true, given that we got a significant result. And Bayes' rule is the formula for calculating that, and it allows us to switch the order of what we're conditioning, this H1 and this P less than alpha. And so we get a result that is in terms of quantities that we know or can think about giving values to. So in the numerator we have this is power, the probability that you get a significant result given the alternative hypothesis, and then this is multiplied by the prior probability of the alternative hypothesis. So the way to think about that is, what do we think the chances are that the alternative hypothesis was true before we ran this study? And we'll come back and I'll say something a little bit more about that prior later. And then in the denominator, we have this first term is the same thing as the numerator that we just talked about. And this other term in the denominator is the probability of a type 1 error. It's the probability that we got a significant result given that the null hypothesis was true times the prior probability of the null hypothesis. So that's in some sense the answer to a question we might be interested in, which is the probability that there really is an effect, that the alternative is true given that we got a significant result. But I'm going to do a little bit more algebra because I want to write it in a form that's particularly simple. So I'm going to calculate also another probability, which is analogous. This is the probability that the null hypothesis is true given significance, which has a name in the literature. You'll see it referred to as the false positive report probability. And the calculation is the also by Bayes' rule. It's the same formula as what we got above, except that now the numerator is the second term in the denominator rather than the first term in the denominator. And the nice formula that we're going to get on the next slide comes from dividing this first formula by the second formula. And the reason that's going to give us a nice result is that the denominator in these two fractions is the same, and so they're going to cancel out. So when we do the division, we get that the relative probability of the alternative to the null, or the odds of the alternative hypothesis relative to the null, given that we got a statistically significant result, is the odds that we would get a significant result under the alternative relative to the null times the prior odds. So so we can give this a name. In some work that I've done, my co-authors and I have called this the pre-experimental odds, because it's basically the odds for the alternative that you would get from a significant result. And it's pre-experimental in the sense that we don't know what the actual p-value is yet. We're just saying how strong would the evidence be from a significant result if I ran this experiment and got something significant. Then this term is what we call the rejection ratio, and this is the prior odds. So the rejection ratio is this, we're rejecting the null hypothesis, and it's the ratio of the evidence for the alternative relative to the null. And what's particularly nice here is that this rejection ratio is just the ratio of power to the significance threshold. And we can interpret it as the strength of evidence from statistical significance, because what this formula is telling us is whatever we came into the study thinking, whatever our prior odds were of the alternative relative to the null, the rejection ratio is how much we should update based on getting statistical significance in order to tell us what our beliefs ought to be now that we've gotten a significant result, what our kind of posterior odds should be, given that we had a significant finding. And so that how much we should update is just power divided by the significance threshold, which I'm calling the rejection ratio. And something I want to highlight here, just to avoid any confusion, is that one of the concerns people have about Bayesian statistics in general is that you need to do a fully Bayesian analysis, you need to specify prior beliefs. And people wonder, well, where are you going to get prior beliefs from? One nice thing about this approach to strength of evidence is that our focus here is not on the prior beliefs. We're interested in the rejection ratio, and the rejection ratio doesn't depend on prior beliefs. So whatever your prior beliefs are, the rejection ratio is how much you should update. So we can talk about the rejection ratio as the strength of evidence from significance without having to worry about the question of what your prior beliefs might be or where they come from.
Dan, if I may interject with a question here.
Yeah.
Sharon is asking, how does the rejection ratio relate to a Bayes factor?
That's a great question. And let me defer it because I'm going to talk about Bayes factors in the second half of the talk. The short answer is the Bayes factor is about the probability of observing a particular p-value or observing a particular test statistic or something. It's the relative odds of that for the alternative relative to the null, whereas the rejection ratio is not about a particular p-value, but about p being less than alpha. There's a whole region of p-values.
Thanks.
Yeah. Okay. So let me show a picture for what this rejection ratio is. So remember, this is the relative likelihood of a statistically significant result under the alternative relative to the null. So here's what a way to think about it graphically. What I'm showing you here on the x-axis is estimated values for our parameter, what I'll call theta hat, and the y-axis is probability density. So the red curve is the probability density for our estimate under the null hypothesis. So if the true value of theta is 0, then the most likely value of our estimate is going to be 0. But there's some distribution around that because there's noise when we sample. So we could get, positive estimates or negative estimates, and we're going to get some distribution, which, we might think is normally just a normal distribution, and it's going to be centered at 0. So that's what this red curve is showing. The blue curve is showing the probability density for our parameter estimate under the alternative hypothesis, where I'm assuming that the alternative is some positive, true value for theta. So if that's where I'm centering this distribution for the alternative hypothesis. Now, statistical significance means that we get an estimate which is larger than some threshold. It's large enough that our test statistic is above the threshold for significance. So that is, this value here, and so the rejection ratio, so the probability that we would get a significant result under the alternative hypothesis is this whole region of this blue distribution to the right of this threshold. So that's going to be this blue area plus the red area. The probability that we get a significant result if the null hypothesis is true is the area of the red curve to the right of this area. So that's the red region. And so the rejection ratio is the ratio of those two things. It's the blue area plus the red area divided by the red area. So it's the relative likelihood that we would end up in this region of, getting this kind of estimate, a theta hat, which is significant if the alternative were true as opposed to the null. Okay, so here's some simple calculations, and I'm taking here, just as to take a concrete example. Say we're talking about an experiment in social psychology, and it's a simple experiment where we just have a treatment group and a control group, and in each group there's a sample of size n, and I'm going to take for an effect size a correlation between treatment assignment, a 0,1 variable, and the dependent variable of 0.21. So that's one way of evaluating effect sizes, which is common in social psychology. And the reason I'm picking 0.21 is that there was a meta-analysis done about 20 years ago that of all research up to that point in social psychology, and they concluded that that was a typical effect size, a kind of average effect size. So, so what I'm calculating in this table is, for given that effect size, what our power is, and also the rejection ratio. So this first column here says if we had 10 people in the treatment and control group, our power would be 25%, and the rejection ratio would be about 5, which means that a statistically significant result gives us about 5-to-1 evidence in favor of a true effect. So we should update whatever our prior odds were by a factor of 5. 30 is an interesting case because you often see, especially in older textbooks, a recommendation that experiments have at least 30 people in each condition. In that case, power is 50%, and the rejection ratio is about 10. Another interesting entry in this table, I think, is 65 people per condition, because that's what you need for 80% power, which is often considered a threshold for adequate power. So one thing to note in that case is that actually 65 people per condition is pretty large relative to, at least traditionally, to the size of experiments in social psychology. So that tells you that, if we take seriously this typical effect size estimate, that most experiments, at least most classic experiments in social psychology were, had less power than that. And another interesting thing to note is that the rejection ratio in the case of 80% power is 16. So that makes sense because the rejection ratio is the ratio of power to significance threshold. If power is 0.8 and the significance threshold is 0.05, that ratio is 16. So, if we follow those standard conventions, what we're getting from statistical significance is 16-to-1 evidence from statistical significance in favor of the alternative hypothesis. The last thing I want to point out, as I'm going to come back to it later, is the extreme end of this table, which is even if we get a big enough sample that we have 100% power or nearly 100% power, the rejection ratio is finite, it's bounded, and it's bounded in this case by 20. And that makes sense because the ratio of power, which is 1, to significance threshold 0.05, is 20. So that's the biggest rejection ratio we could possibly get if we have a significance threshold of 0.05. Okay, so let me just say something about prior odds, because even though I said we can talk about rejection ratios without specifying our prior odds, I think we really should strive to be more Bayesian than that. And if we want to think about how much evidence there is from an experiment, we want to use what we can say about the prior odds in addition to the rejection ratio to think about how strong our beliefs are in favor of an effect. So there's lots of things that can go into prior odds. The scientific consensus before you do an experiment, or other evidence that's closely related could go into prior odds. A lot of the bad research practices that I think you've already talked about in RT2, like p-hacking and multiple hypothesis testing. One way to think about them is that they essentially reduce the prior odds by changing the population of tests that are being reported. Okay, but prior odds can be very different across different contexts. So for example, for medical treatments where you've already had stage 1 and stage 2 trials and you're going into a stage 3 trial, you might already think that there's, like 50% of stage 3 trials end up producing successful evidence for an effect. You might think then the prior odds are about 1-to-1 in that context, whereas in for another context, like the genetic work that I do, where you're scouring the genome and there are thousands of potential genetic variants, and you're only some of them matter for a trait that you're interested in, the prior odds might be 1 in 10,000. So it's really going to matter a lot, and you can think about it for the kind of research that you do. What's the likelihood that there really is the kind of effect you're looking for? So there's actually some evidence in social psychology that prior odds are about 1 in 10 on average. This is from the big replication project that was published in 2015. That then some statisticians subsequently analyzed and estimated, based on the results of the replication project, that if you went back and you looked at the original papers and estimated how likely was it that the effect they were looking for was really true, the estimate was 1 in 10. So actually, that's pretty bad. Basically, like a 10% prior probability of the alternative hypothesis being true. There was another analysis that also gave 1 in 10 as an estimate, and that was from a study that used prediction markets and basically had experts bet on likelihood of replicating some of the earlier results. So there's some convergent evidence that 1 in 10 is not bad, at least for social psychology that was published up until that time in top journals. It's been argued that 1 in 10 is also about right for cancer clinical trials. In experimental economics, there was also a replication project on a smaller scale, and the replication was better than in social psychology. So, you know, I would say that that kind of evidence suggests that the prior odds are more like 1 in 5 for experimental economics. So these are the kinds of numbers I'm going to use, you know, to calibrate the calculations that will for prior odds going forward. So coming back then to this kind of calculation, if you think the prior odds are 1 in 10, then a rejection ratio of 10 to 1 will mean that it's just moving your beliefs to 1 to 1. So it means that after you ran your experiment with 30 people in each condition and you got a statistically significant result, or, you know, if you were planning a study where that was going to have 30 people in each condition, then what you should think to yourself is, if I got a statistically significant result from that study, then, and you know, I was testing a kind of typical hypothesis where my prior odds would be 1 to 10, then after a statistically significant result, I should now think it's 50-50, that there really is an effect. So maybe that's not convincing enough. Maybe that means that you would want to do a study with more power. You would want to do multiple studies to get those posterior odds higher. Okay, so let me summarize some implications from this part of the talk. First is that power matters for the strength of evidence from statistical significance. That is contrary to some common fallacies that you sometimes hear. People might think that if a result is significant, then power doesn't matter anymore. And sometimes you even hear people go further than that, and they say, if you get a significant result despite having had low power, then it's like you've overcome adversity. It's like even more convincing that you got a result. And that's just not true. If power was low, then statistical significance is less meaningful in terms of evidence. Although I've been talking here about this null hypothesis paradigm and you know, rejecting or not, the same kinds of issues carry over if you're interested in parameter estimation. There's a very nice paper I recommend by Gelman and Carlin that talks about that. And they show that if you have low power, that means you're more likely to get the wrong sign of your estimate, and you're more likely to exaggerate the effect size. The second lesson is that if your prior odds are low, then you should consider having a lower statistical significance threshold than 0.05. And that goes back to this point that the rejection ratio is bounded above by 1 over alpha, because your power can't be higher than 1. So your rejection ratio can be at most 1 over alpha. So if alpha is 0.05, that rejection ratio can't be higher than 20. And so if you're dealing with a particularly unlikely kind of phenomenon, like let's say you're interested in my context of genetics, you know, we couldn't use a significance threshold of 0.05 because it just, you know, results that were statistically significant wouldn't be convincing enough. So in genetics, there's a lower significance threshold that's used, 5 times 10 to the negative 8th. So that ensures that results are sufficiently convincing. And you know, I think that lesson can carry over to other contexts as well. Okay, so let me move on to the second part of the talk, which is p-values. And this is, you know, now you've done the study, you've done some analysis, and how should we interpret the evidence from a p-value? So the problem here is that you know, a p-value is asking the wrong question, or a different question anyway, than the one that we ultimately would like to answer. The p-value is asking the question, to what extent is our data inconsistent with the null hypothesis? But often the question we're interested in is what I'll call the strength of evidence question. We want to know how strongly does the evidence favor the alternative hypothesis relative to the null hypothesis? And the alternative hypothesis doesn't enter into the calculation of the p-value, so it doesn't directly answer the strength of evidence question. So, you know, but people often try to use p-values to answer the strength of evidence question and often misinterpret the p-value as giving stronger evidence than it actually does. And as I mentioned, the p-value doesn't take into account inconsistency with the null hypothesis, with the alternative hypothesis. And the other problem in the way people often interpret p-values is that they treat a p-value of a given level, like 0.05, as if it's a p less than that level. So they treat, you know, a p-value of 0.49 as interchangeable with p less than 0.05. And, you know, that's not right. It's actually much more information when you know what the p-value is than just knowing that the p-value is in some region. So this, you know, I would argue contributes to some of the problems with reproducibility. I'm going to argue that p-values near 0.05 are actually pretty weak evidence, but results with those p-values are treated as having been established. And so then people are surprised, you know, we shouldn't be surprised that they don't replicate. You know, those kinds of results are much more likely to be false positives than people realize. Okay, so this comes back to the question from earlier. Bayes factors are a way to think about the answer to the strength of evidence question. And we want to know, if we observe a p-value of p obs, what are the odds of the alternative relative to the null? And if we do the same kind of calculation as before, but this time using p equals a particular value rather than p less than a threshold like alpha, the same kind of calculation using Bayes' rule gives us this formula. The posterior odds equals, and now this term that previously was the rejection ratio, now that we have p equals p obs, is called the Bayes factor. And one technical modification we have to make here is that because the p-value is continuous, we can't use probability here. We have to use probability density, but it's the same idea, and then times the prior odds. And I want to highlight here the same thing I highlighted earlier about the rejection ratio, which is that even though this is a Bayesian approach to interpreting things, our focus is going to be on the Bayes factor, and that doesn't depend on the prior odds. You know, whatever the prior odds are, the Bayes factor is a way of thinking about the strength of the evidence, you know, it's telling you how much you should update your prior odds to your posterior odds, but itself doesn't depend on what your prior odds are. Okay, so just like I gave you a graphical way to interpret the rejection ratio, I want to give you a graphical way to interpret the Bayes factor. Remember, the difference here is that it's p equals some value rather than p in some region. So with the same kind of figure as before, where we have this red curve being the distribution under the null, centered at 0, and some alternative distribution for what we might observe that's centered at some positive value or alternative. Now what we're saying is pick some p-value, say that the p-value 0.05, and that's going to correspond to some value for for what we observe, and then we're going to have you know, some density of having observed that under the null, and some density for having observed it under the alternative, and the Bayes factor is the relative height of those densities at that particular p-value. So that's the relative likelihood of having observed that value under the alternative relative to the null. So what we would like to do then is convert from a p-value to a Bayes factor, because the Bayes factor gives us this answer to our strength of evidence question. But we already know that that's going to be impossible, because the p-value you can calculate just based on the alternative under the null hypothesis. The alternative doesn't enter into it. So there's not enough information in the p-value to calculate a Bayes factor. But what we can do is calculate, calculate a bound under some assumptions about the alternative hypothesis. So here's an example of how we can do it. Let's consider a case where our data, let's say this is the standardized mean for an observation. It's drawn from a normal distribution with mean theta and variance 1. So this is actually quite a general kind of specification because we can get the variance of our draw to be 1 by standardizing, and then we're just going to say that under the null the value of theta is 0. And if we're considering a one-sided test, every for any p-value, we can translate that to a particular draw of our sample mean, or a standardized sample mean. And we could then say that set as our, say we observe some value for this draw of our sample mean in our data. If we then say that our alternative hypothesis is going to be whatever we actually got, we're going to set our theta equal to what we got, that will give us an upper bound for the Bayes factor, because this is cheating. We're going to use our data to say what our alternative hypothesis is. That's giving the best possible case for the alternative hypothesis. We're going to calculate the Bayes factor based on the alternative being what we actually observed. So this is going to tell, under a more realistic alternative, the likelihood of the chance of getting this is going to be lower than under this alternative. So what's that going to look like in terms of our picture? We have our null, which is centered at 0. And then, well, let's do this for the case of where our actual data was exactly at a p-value of 0.05. So we ran our analysis, we got a p-value of 0.05. If that was a one-sided test, and we're talking about the standardized mean, that's going to correspond to a value of 1.6. This is the threshold for the t statistic in a one-sided test. So that's where our data actually is, exactly significant at the 0.05 threshold. And then if we make that into our alternative hypothesis, we're going to take an alternative that has its highest possible value at the point that we observed. And then we're going to calculate a Bayes factor, assuming that that was our alternative hypothesis. So that Bayes factor is going to be 3.9. So what that's saying is, if we cheat and we use our actual data to tell us what our alternative hypothesis is, then we have evidence in our one-sided test of 4-to-1 in favor of the alternative. If we had a more realistic alternative, so if we moved this H1 to be centered somewhere else, we're clearly going to have a lower Bayes factor because we're going to have a lower density at this point. So this is an upper bound. 4 or 3.9 to 1 is the strongest possible evidence we could get from a one-sided test from a p-value of 0.05. Now, you could do this kind of calculation for different p-values, and you could do it for a two-sided test. It's going to be a little more complicated to draw the picture in that case. And you could also do it under different classes of alternative hypotheses. I mean, I really did the alternative that was the most favorable by using the data. You could make some more restrictive assumptions on the alternative. And statisticians have done that and done this kind of calculation of upper bounds under different classes of assumptions about the alternative hypothesis. And so what I'm showing you on this graph is a summary of all of that. So the x-axis here is different p-values ranging from 0.001, here's 0.005, 0.005, here's 0.05, here's 0.1, which is often called marginally significant. The y-axis here is Bayes factors, and the different curves are showing different ways of calculating these upper bounds. So this black line corresponds to the way that the kind of calculation I just did, which is kind of the upper envelope of all of these other ways of calculating upper bounds, because it's really, taking the really best case scenario for the alternative, and more realistic classes of alternatives are generally give less, less good Bayes values than that. But I want to highlight that that for a p, and this is also for two-sided tests, which is why the number, instead of being 3.9 for the black line, comes out to be 3.4. And what I want to highlight is, for a p-value of 0.05, pretty much no matter which way you calculate this kind of upper bound, you're getting a number in the range of 2.4 to 3.4, so about 3. So we should be thinking of a p-value of around 0.05 is giving us 3-to-1 evidence in favor, at most 3-to-1 evidence in favor of the alternative relative to the null. Might be less than that, depending on what the actual alternative is, but in a good case scenario for the alternative, or best case scenario, it's about 3-to-1 evidence for the alternative. Okay, so I think the picture is actually probably the most useful thing and worth keeping in mind. But there are some simple formulas that can be used as well for calculating some of the curves. So like I'm showing here, what may be the most simple formula for one of these kinds of calculations for an upper bound, and then you can plug in some numbers for different p-values and calculate what the upper bound would be. Let me draw out some implications from this part of the talk. So one thing I want to highlight again is that there's more information in knowing what the p-value is than knowing that it's less than some threshold. And so you should be reporting p-values, not p less than 0.05 when you're actually doing data analysis. And in fact, it's important, it really matters, because oftentimes when people are reporting p less than 0.05 in papers, what they really mean is the p-value was close to 0.05. So 0.05 is the smallest number that I can report such that it's true to say p is less than 0.05. But that's misleading, because a p-value of 0.05 is much weaker evidence against the null hypothesis than the fact that p is less than 0.05. If all you knew was that p is less than 0.05, that includes a lot of possibilities, like really, really tiny p-values that would be very, very strong evidence against the null, whereas p equals 0.05 is actually, just one of those possibilities, and is the least evidence against the null of all of the p-values less than 0.05. And in fact, what we just saw in this graph on the previous slide is that it's pretty weak evidence. A p-value of 0.05 is at most 3-to-1 evidence of the alternative relative to the null. And I guess I'll just mention one other thing from this graph, because you may have heard about a paper that I was part of that was arguing for changing the significance threshold from 0.05 to 0.005. And you can see in this figure the kind of logic behind that. People naturally think that p-values of 0.05 correspond to something like 20-to-1 odds. It's kind of an incorrect intuition people have that it corresponds to like 20-to-1 odds against the null hypothesis. And what this figure shows is that if that's really what you're aiming for, then it's the p-value of 0.005 that corresponds to that. That's where you get upper bounds that are around 20-to-1. Okay, so I guess one other implication just worth mentioning is, because 0.05 is such weak evidence, if we take seriously that the prior odds for, a study is 1 to 10, then a p-value of 0.05 is such weak evidence that it should still leave you thinking that there's, even after getting a p-value of 0.05, that there's 3 to 1 evidence against there really being an effect, because you would need, if you multiply 1 to 10 by 3 to 1, you still are around at 1 to 3 odds. Okay, so let me end with some suggestions for doing reproducible research. In the study design phase, first of all, ask yourself, given the prior odds for the kind of effect that I'm looking for, is 0.05 the right significance threshold? Because if I use 0.05, the upper bound on the rejection ratio is 20. If prior odds are low enough, I might need a higher rejection ratio than that. So in that case, I should have a lower significance threshold than 0.05. Once you've determined the significance threshold, then ask yourself, what is my power given the anticipated effect size? And really calculate it and really report it, because that's going to be relevant for evaluating what kind of evidence you could have hoped to get out of a study, get out of the statistical significance, given that level of power. Once you've done the analysis, I think that the key thing to keep in mind is this figure. This is probably the most important figure in the talk, and that is, how strong is the evidence really from that p-value? And this tells you 0.05, it's at most 3 to 1, 0.005 at most 20 to 1, and you can do the mapping for whatever p-value you actually get. And I think you talked about pre-registration already in RT2. I think it's valuable to, in addition to pre-registering your planned analyses and data coding and all of that, also pre-registering what your prior odds were, what your significance threshold is that you're going to use, what your anticipated effect size is, what your power calculations are. I think all of that adds credibility to the evaluation of the strength of the evidence from the study. Okay, so I've listed here some of the references in the paper in case you're interested in reading more. So I'll stop